Thank you very much. I'd like to start by acknowledging my co-authors, my Banawan, my PhD student, who unfortunately was unable to attend, Dr. Wang, who is our collaborator from Quebec City's Office for Huawei, and my colleague, Professor La Rochelle. And of course, as mentioned, I'm at the Université Laval and within the Center for Optics, Photonics, and Lasers. So I'll be talking to you today about why it's important to model degeneracy in high contrast ring core fibers, and I'll be explaining the differences between the proposed model and the previously reported models, and of course giving you some details on how those models are evolved. And I'll give you some simulation results that highlight the differences and why we think they're significant. So we're interested in orbital angular momentum fibers. What I'm showing here is the intensity profile and phase profile for different order modes of OAM. The reason we're interested in orbital angular momentum is for spatial division multiplexing applications. The objective is to reduce the modal interactions by exploiting these modes. So, for instance, they're targeting 2x2 MIMO or completely MIMO-free transmission in spatial division multiplexing, and this is what distinguishes it from exploitation of linearly polarized modes. And so we can see that if we want to exploit these for MIMO-free operation, of course it's important to be able to model exactly what the degeneracy is within the fiber. So I'll start by just giving you the equations here for OAM fiber modes, and you can see they're formed from the eigenmodes within the fiber, and in fact they're formed from a linear combination of the even, that's the E up here, and the odd solutions to Maxwell's equations. And because you'll notice that there are some plus and minus signs in here, and I just want to point out that they refer to two things. Up here in the superscript, it has to do with right or left polarized circular polarization, and so that's sort of indicated in this diagram in the blue. And then the other plus and minus is the order of the OAM mode, and that's sort of shown in the red. And I mention this just because it'll help interpret some of our results. You can see that sometimes the rotation of the phase front and the rotation of the polarization is in the same direction. We call that the aligned, spin orbit aligned mode. And the other two cases are the anti-aligned modes. So often we'll group the discussion about the mode characteristics in this manner, and that's what I'll be doing today. So what's interesting about OAM compared to LP modes in exploitation for SDM is the fact that in this linear combination, by default, the eigenmodes have the same propagation constant. And this is what leads to the good characteristics of OAM. But of course, this is true in a perfectly symmetrical circular ring core fiber. But we know that, in fact, nothing is as perfect as we'd like it to be, and so there may indeed be some differences in the effective index of these two eigenmodes. In fact, Professor Wilner's group has simulated several years ago elliptical deformation in a ring core fiber and shown that there is a variation in the walk-off length with the amount of ellipticity introduced into the fiber. So what we're going to do is take this concept and push it farther and put it into a model for propagation. And we believe that the differences that we'll be presenting between previous methods and our methods has their root in being able to capture this effect in the new model. Because ultimately this is what leads to the coupling. So I'll start by just saying that there have been demonstrations of MIMO-free transmission over a kilometer length of high index contrast ring core fiber. And in this case, it was an experiment with Ramachandran's group, and they exploited 3 OAM mode orders, 5, 6, and 7. You can see that they deliberately targeted the higher order modes because they found them to be more stable. So our questions when we moved to going to our modeling was which order modes maintain their orthogonality to permit MIMO-free operation, and how do these OAM interact during propagation that will help us predict this. So we'll go into now the equations. The method of simulation to date has been based on perturbation theory, so that you would actually calculate the coupling coefficients between modes from an overlap integral of the type you see here. So you would start from numerical simulations for the particular fiber design, assuming perfectly circular ring, and you would get your mode profiles, and then you would perturb them with this factor epsilon, and you would calculate your coefficients from that. However, it's a poor model for OEM fibers because it assumes a little too much symmetry in this perturbation model. And because of that, it doesn't capture the differences, for instance, between low and higher order modes. And clearly in the experimental results, we saw that higher order modes were of more practical interest. So both quantitatively and qualitatively, we need a better model for this. So I'll start by showing you some old predictions, and then I'll show you my new model and how, what the advantage is in using this new model. So we start, in order to be able to compare with previous results in the literature, we take a fiber that was actually designed in my lab, which has an air core and a ring-guided section of the fiber. And previous results, they would take all of make a matrix for the coupling coefficients. So on the left and the bottom, we have all the modes that are supported. The A is the aligned, the AA is the anti-aligned. And you can see the scale in dB. Blue means there's no coupling. Bright yellow means there's significant coupling. And ideally, you would like to have blue everywhere and just yellow on the diagonal for an identity matrix. So this was the simulation of this fiber, which was produced earlier. And you can see, of course, the behavior is much more complex than an identity matrix. So I've highlighted in darker order some of the things I'd like to point out are the results of this mode. First of all, I put these slash marks, hash marks, because on the diagonal, we assume that the anti-aligned and the aligned modes are degenerate, and it's not actually examined at all in the model, it's just assumed. And so we assume that there's complete degeneracy within these. But of course, that contradicts what we've seen in experiments, that in fact, MIMO-free transmissions were possible. So clearly there's a need for a better model in this regard. And also, if you'll observe, between, for instance, the fourth or the third and seventh mode, you're getting the same results near the diagonal. And in fact, there were higher order modes were favored in the experiment for a reason. So this is what we found did not help us with this model and why we moved on to another one. So in the new model, what we use are the coupled mode equations. We assume that that there are a set of eigenvectors that describe the relationship between E, which is the unperturbed mode profiles, and E tilde, which are the perturbed models, assuming that we have profiles, assuming that there is an elliptical perturbation in the ring core. So we can solve or exploit the coupled mode equations in order to come up with a vector representation of the relationship between. Here we have the different modal propagation. Remember, I said because of the perturbation, these modes are actually going to propagate at different speeds. So if we look more, that this K is the coupling matrix that I just displayed for you and what it is we're trying to solve for. So before, these elements of this matrix were calculated using an overlap integral. Now we can see there's a different methodology used in order to calculate them. In the former method, we only calculated the E, we only exploited the mode profiles from the perfectly circular fiber. Now we actually go and we calculate it twice. We run through COMSOL, we have the perfectly circular, we get the E, and then we also perturb it with a certain level of ellipticity, and we come up with the perturbed mode profiles. So from these two, we're able to solve this system of equations to come up with a different method for for calculating the coupling coefficients, and where now we have directly in our equations the difference, the perturbation in the propagation constant. So let me show you results for the same fiber simulations. So on the right, I have what I showed to you before, and we can see we get very different predictions on what the coupling behavior is for this fiber. And most importantly, we can see the degenerate mode coupling and how it changes with mode order. So we can see a difference in evolution from the lower order modes to the higher order modes. And even more importantly, if we look at the coupling matrix within one of the aligned or anti-aligned groups, we can see here that it looks more like an identity matrix. So we can see that the degeneracy is not present in this mode, which is in alignment with what we have observed experimentally. This is the first step. You make your estimate of the coupling matrix, but once you have the coupling matrix, of course, you want to see how that evolves, and during the evolution, we again take advantage of our knowledge of the propagation or the effective index separation perturbation. So we use an approach much like what has been used in the previous method. We break our propagation into very small rotations of the fiber. Use a slightly different method of calculating the rotation than what was done in previous works. So for instance, in this case, I'm going to assume that I launch one mode, the +4 anti-aligned mode. And now on the x-axis, what we have here is a propagation distance. So I launch it all on one mode, and as it propagates, some of the power is leached off of this mode and goes to other modes. What you don't see here is actually both the anti-aligned contributions, the +4 and the -4, have completely mixed even after a very, very short distance, because they are degenerate at this lower order. Now if I start looking at the contributions where the energy is leaked to, which modes have they leaked to, we can see the contributions, the most significant leakages to the same order mode, but to the aligned versus the anti-aligned. So this is for a lower order mode 4, and now let's see what happens. I should mention that in this case we see the degeneracy in the anti-aligned mode. So this is an example where the OAM would require 2x2 MIMO. You couldn't do MIMO-free transmission on this one. So now if I go to a higher order mode, 7, I have basically the same situation, except now when I launch +7 anti-aligned, it does not become degenerate. In fact, it stays independent, if you will, from its anti-aligned partner for a certain distance, which is predicted. Of course, in this model, we assumed 1% ellipticity just to see if we could discover the differences, and we would need experimental results to validate if this was the correct parameterization. But it's the qualitative behavior at the very least which is of interest here. So in fact, if we look at where in these higher order modes the leakage is going, we can see that it's not even to the most related, the other 7 order mode. It's to in fact the 5. And this is not too surprising since there is coupling between modes, the strong coupling between modes at a difference of 2 in the order number. So interesting is there's no degeneracy originally, so you could do MIMO-free transmission in this case. And the crosstalk to the opposite topological charge is not strong, which is, I think, a surprising result. Okay, so just to conclude, I'd like to say that our model captures the coupling within an aligned or an anti-aligned pair. It quantifies the difference in the coupling between anti-aligned and aligned modes as we change, especially with different mode orders. We do this, results that I've presented were for a specific percentage of deformation, and for this deformation we could predict at which order. So we could say that order 4 there was degeneracy, by 7 there was not, and of course if we could parameterize this better we may be able to predict the experimental results. Lower order modes will require at least 2x2 MIMO, whereas higher order modes could potentially have some distance for which they were MIMO free. Okay, thank you for your attention.